Hi, welcome to this lecture. Now we will continue hard bake. Okay, it will become, the photoresist will become stronger. Again 1 minute on hot plate. Once you do that, you have this pattern of the photoresist which is ready for the inspection, Now the question is that what I get out of patterning the photoresist, isn't it? Why? Why should I pattern the photoresist? So, I will give you an example of that. So, this is the positive photoresist, right, after following the steps which we learned in the previous slide. Hard bake followed by the pattern recognition, isn't it? This is the slide, this is the image. Now, let me give an example of why we are interested in patterning this photoresist. So, now let us take an example where instead of silicon you have silicon dioxide. So, oxidized silicon wafer. So, this is your SiO2, okay, silicon dioxide on silicon with help of thermal oxidation, not evaporation, okay, thermal oxidation, CVD technique, thermal oxidation. Okay. Now, everywhere let us draw silicon dioxide. So, on the silicon dioxide you have positive photoresist, on the silicon dioxide you have positive photoresist, and then there is a mask, and then when you expose the photoresist with UV light followed by developing it, you get this pattern, and finally you end up with this pattern after you do the hard bake. Easy? Correct? Now, what happens is, if I dip this wafer, if I dip this wafer in SiO2 etchant. Etchant is a material, chemical that reacts with the material and etches it, right. So, silicon dioxide etchant is buffer hydrofluoric acid, BHF. See, if I dip this wafer, in BHF, what will happen? Is that the photoresist which is on the silicon dioxide, if I dip the wafer in BHF, the photoresist on the silicon dioxide let me try to draw it here. The silicon dioxide which was protected by the positive photoresist, right. When you dip this wafer, this one, let us say this wafer name is A. So, when I dip wafer A into buffer hydrofluoric acid, BHF, this is a silicon dioxide etchant. The silicon dioxide which was protected by the photoresist will be there, and when the silicon dioxide which is not protected by photoresist will get etched. You can see. Now, if I dip this wafer which I say B, right, into acetone, 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 okay. if I dip the wafer B in acetone, what will happen, you know? Acetone is known as a photoresist stripper, it will strip off the photoresist. So, what will I have? The next step, if I dip B into acetone, I will end up with a silicon dioxide patterned on silicon. So, that is, let us say it is C. So, the wafer, that is step 1 where we started, you can see silicon dioxide is on entire silicon substrate. When we did this photolithography, we end up patterning silicon dioxide in this particular fashion, is not it? We end up patterning silicon dioxide, as you can see on this slide. This is the beauty of lithography, and then once you do that, you can heat it silicon dioxide. So, the point is, by doing this photoresist patterning, right, and if there is a material which is below the photoresist which is the area which is covered by the photoresist will be protected, the area which is not covered by the photoresist get exposed to the etchant and will get etched, and you can finally pattern different kind of materials. Okay. I hope now you understand the lithography technique, where you start with wafer cleaning, pre-baking, photoresist pre-cleaning, spin coating, soft bake, alignment and exposure, development, hard bake, followed by the pattern inspection. So, let us understand again from the slides. So, wafer cleaning and pre-bake, and then once we finish this photolithography section, I will start explaining it to you how to fabricate different devices. Okay. So, the wafer cleaning and pre-bake includes silicon wafer cleaning methods, which is scrubbing, this is bubble jet N2 plus H2O, followed by high pressure rinse, sonication, then dehydration, which is pre-bake, and priming, high temperature baking to remove moisture after wafer cleaning process, and priming is to improve the photoresist adhesion onto the wafer. It follows HMDS, and then to heat between 200 and 250 degrees centigrade, and then for 60 seconds. So, this is what it happens, as I told you, in terms of the wafer cleaning. In terms of the lithography, if it is if you coat the photoresist, right, and then you expose the photoresist with help of a bright field or dark field mask, the area, assuming that is a positive photoresist, the area which is not exposed becomes stronger, which you can see from this particular image. So, now if you understand what is photoresist, photoresist is solid organic material. It is used to transfer the design pattern or desired or design pattern to the surface, changes photosolubility due to photochemical reaction exposed to light. For example, in case of negative photoresist, the unexposed region will become weaker. In case of positive photoresist, the unexposed region will become stronger. In case of negative photoresist, the exposed region will become stronger. In case of positive photoresist, the exposed region will become weaker, and so on and so forth. What should be the parameters of the photoresist? So, it should have a high edge resistance, good adhesions. What is high edge resistance? So, let us go back to the slide which is here. Now, we see here the photoresist when it is dipped in the buffer hydrofluoric acid. So, when you take this wafer A and dip in buffer hydrofluoric acid, the photoresist is not getting affected. You see, the photoresist is intact, only the silicon dioxide is etched, right. So, it should have high edge resistance, that is what high edge resistance means, and good adhesion to the wafer. How it is done? So, wafer is held onto the vacuum chuck. We dispense about 3 to 5 ml of photoresist. First we start with a slow spin, so that uniform coating is there, then you ramp up the speed as much depending on what kind of thickness you desire for the photoresist. It is spread by a centrifugal force, and the quality measures are time, thickness, speed, uniformity, and some of the defects are particles that are there onto the wafer. These are some of the negative photoresist and some of the positive photoresist. Nothing to really remember this, because if you can Google it, you will find out different photoresist data sheet from where to buy and every other things. And again, this is what I have shown it to you in terms of how the mask looks like, how the bright film mask looks like, how the dark field mask looks like, and how the different mask will create different kind of pattern depending what kind of photoresist you are going to use. This is very simple example where it shows that if you have mask which is bright field mask like this, and if you go for positive photoresist, you can regain the same pattern. You see, this pattern is same as your mask. This is mask and the pattern, let us say we call as P, then we have the same pattern P here when we go for positive photoresist, where we have P inverse on or P star, which is the inverse pattern of whatever there is a mask. So, wherever there is a bright area, it becomes black, and black area becomes bright, right. So, dark or bright in that terms. So, negative photoresist, positive photoresist, the use of it when we use bright field mask and dark field mask. How we should use a photoresist, like I said, these are some of the ways to use it. We already have seen the how the photoresist parameter should be. This particular image will help you to further understand that there is a spindle, there is a chuck, vacuum chuck here, and then vacuum pump is there. So, the spindle will rotate, but because the wafer is holded to the vacuum chuck, wafer will not fly, and you can dispense the photoresist about 3 to 5 ml, and then you can see that with spin speed, as you increase the spin speed, the thickness of the photoresist starts decreasing, so that at a higher spin speed or higher RPM, the thickness is lower. So, in a way and further, if you want to really understand, then it is thickness is inversely proportional to the square root of spin speed. Higher viscous photoresist coated with lesser thickness, the higher spin speed will result in higher thickness, right. This is obvious. Soft baking, like I said, if you go for most of the photoresist, again photoresist comes with data sheet, but if you go for positive negative photoresist, it is 90 degree centigrade 1 minute on hot plate. So, this is a soft baking temperature, time, and in hot plate, but if it is oven, then the time would differ. The time would differ if you load the wafer in oven after spin coating the photoresist. What does soft bake does to the photoresist? So, partial evaporation of photoresist solvents improves adhesion, improves uniformity, improves etch resistance, optimize light absorptions or absorbance, and characteristics. These are the characteristics of the photoresist. When you expose the photoresist, what happens is that through the light, which is UV light, passes through the lens, and then the ideal light intensity you can see here. However, the diffracted light collected by the lens is shown in this particular case, and there is a less diffraction after focused lens after focus by the lens. So, we get this kind of pattern from the when we expose the photoresist by UV light through the photolithography system. Again, for you to understand how the photolithography system works, including how to load the mask, how to load the wafer, how to spin coat it, how to expose it, we have a laboratory recorded video, so that you have more understanding about the entire process. When you develop the photoresist, the time is very important. So, what we call is a photolithography recipe. Recipe is that if you increase the time, things will not be how we want to get it patterned. For example, in the terms of, let us say, the development should be for 1 minute. If you go for 50 seconds, right, then you will not get the complete development of the photoresist, which you can see here. I am just giving numbers. Okay, the point is that the time or the recipe is very important. Recipe includes what kind of chemicals you to use, and the process time is important, because if you decrease the time, incomplete development, if you increase the time, over development, and sometimes there is a under development as well. So, the development profiles can be different. Again, negative versus positive photoresist. I think I have given enough examples to you. If you want to quickly show it to you, quickly write down somewhere when such kind of questions are asked, not in just NPTEL exam, but in your university, in your colleges, right. If this course is taught, then this is a way to quickly show what will be the effect of negative photoresist when we are using a particular mask and the positive photoresist on the pattern that we are looking for. Those who are interested in chemistry, they can see this particular slide that the resist has two functions: precise pattern formation, protection of the substrate. Parameters are optical parameters is resolution, sensitivity, which is photosensitivity, index of refraction. The chemical mechanical properties includes viscosity, adhesion, edge resistance, thermal stability, sensitivity to ambient, and several ingredients in eye-line resist, which are phenolic materials, which are the edge mask, what kind of materials are there, what kind of solvents are there. However, for this particular course, we are not bothered with the details of this, but just because if really you want to understand that how the and why the materials would change the property when it is exposed to a light, you can understand from this particular materials that are used, both G line material and I line resist that are used in the photolithography process. Okay. So, let us understand the UV. So, the average energy of UV source is less than the visible range. So, to maintain those, chemical amplified photoresist can improve the efficiency. These are material parameters of the photoresist. Photoacid generator or PAG is converted to an acid by photon exposure. Later in the post exposure bake, the acid molecule reacts with the blocking molecule on a polymer chain, making it soluble in developer and regenerating the acid molecule. So, this is a process when we say that when it is exposed to light, what happens, right, whether it is hardening in the area which is exposed or softening in the area is exposed is because of this particular process. So, the cross linking of the resins helping in hardening of the photoresist. When you go for further hard bake, right, that is what it means. And when we talk about the mask, which is the basics of mask, you can see that the masks generally are designed, because before we get the mask on the glass, right, which I have shown it to you, first you need to design using the software, and the software generally we use is called Clevin, and the beam scans to the blank mask. Mask material can be a glass plate with chromium coated on it. Sometimes mask can be referred as chrome mask because the chromium material is used. E-beam selectively pattern the mask, develop the resist and remove the chrome from the designed area. So, the electron beam will selectively depending on the type of pattern that you have designed in the Kelvin software or using Kelvin software. Mask making should be done with great accuracy and mask must be very clean. Any defect in the mask result in incorrect features in all the devices chips. Again, the mask is actually 5 to 10 times larger than actual feature. The features are reduced or zoomed out during the lithography process. So, it will be called as 5x mask or 10x mask. This is how the mask is fabricated. Okay. But for you just directly come to the point that if the mask is ready for the pattern that you want to design, right, how can you use the mask. And in addition to this design, mask will have the alignment marks and test structures. I will show you multiple masks and how the alignment will work. In fact, let me show it to you here. So, you have mask 1, you have mask 2. We will take the same example that we left in the previous slides. So, you have, and I am deliberately drawing this alignment mark smaller than this is mask 1. This is mask 2, two triangles were there, right, in our earlier pattern, and this was there, right. Now, I take a wafer, I load my mask 1. You understand that this wafer is already spin coated with photoresist soft bake, and then we load the mask 1 onto the wafer and perform the UV exposure. After UV exposure, when you take out the wafer, so we will go here after UV exposure, where when you unload the mask and develop the this wafer or photoresist, you will have. So, your starting silicon wafer is like this, right. This is your 1, but the final silicon wafer will look like this, because you have your mask, right, and this silicon wafer has a silicon dioxide on it. Okay. So, the cross section looks like this. Okay. The cross section looks like this. Actually, you can only see 1 out of 2 things, but still let us draw like this. So, after this, which is your final mask, after your mask, when we use mask 1, then you load this mask or dip this mask in BHF, remove silicon dioxide. So, final pattern you get is this pattern, correct, this pattern. Now, if I take this wafer, right, so I will say now wafer, and this wafer has this pattern, which is silicon dioxide in this particular fashion, right. Now, what I want to do is I want to load mask 2. So, I will take mask 2, again I will spin coat photoresist, soft bake it, and then I will load mask 2. Okay. The mask 2 alignment should be such that it exactly covers this triangle. Okay. How can I do? So, I will align the mask 2. So, let me just. So, the mask 2 this one plus, right, should be here. You see, now the mask 2 plus is smaller than my mask 1 plus. Okay. Mask 2 plus or alignment mark is smaller than the mask 1. Why? So that the mask 2 alignment mark can fit very well on the mask 1. So, that mask 2 alignment mark will fit on mask 1. Alright. That is the alignment mark usefulness, that instead of looking at the pattern that you want to align, we will directly align the alignment mark, so that all the patterns will align automatically. Got it. So, that is the usefulness of the alignment mark. Now, the mask can be on Fe2O3 on soda lime glass, or it can be a chrome mask. A bright field mask, mostly transparent, features will be opaque. I have shown it to you. The dark field mask, mostly opaque, features will be transparent. Again you have seen this thing when we are talking about the mask. Now, let us understand the defect in photomask. Okay. So, the first defect that you see is a chrome spot. You see chrome spot is there. So, this chrome spot within this area. Now, we are talking about the devices which are really bigger in dimensions. When we talk about the chip, right, then within this triangle you will lose many devices. So, any defect is not a good defect. Now, assume that you have a micro heater. So, let us say you have a meander shape micro heater. Now, why is a heater? Because if I take contact pads and this is a, let us say metal, it is a metal, and then if I apply a voltage across this metal, this is nothing but a resistance. So, the current will flow through it, and because of Joule's heating, then we will see the change in the temperature. In this case, this chrome extension will change the resistance of this micro heater, is not it, because this is extended. So, the resistance that we actually calculate depending on the length and the area of the micro heater, right, will change because of the extension. if there is chrome bridging, which you can see here, there will be short circuit, is not it? It will be shorted, that particular lines will be shorted, not allowed. If there is a spin hole, that means that this device can either be the resistance either would not be there, or there will be a gap between any line of this particular micrometer. Pinhole is not a clear extension. Again, if there is a breakage, the resistance value would be different. If there is a clear break, it is a open circuit, right. This is a short circuit, this is a short circuit, this is the open circuit, short circuit and open circuit. So, these defects in photomask are not generally allowed, and not allowed means what? We should be careful while we actually design the mask. So, that are the defects. So, lithography in sequence, right, or lithography sequence is that you start with a wafer, right, then you clean the wafer, right, pre-bake it, so to let the moisture get evaporated, then you spin coat the wafer. After spin coating, you can do soft bake. See, again the words are used in a little bit different format. So, generally you will find pre bake, post bake as one term, or soft bake, hard bake as another term, both are same. Okay. So, either we use pre bake or soft bake, or post bake or post exposure bake or hard bake is the same thing. Just to make sure that we understand that when we start the wafer and we want to pre-bake the wafer to remove the moisture, and that should not be confusing with our soft bake and hard bake. We use term pre-bake when it is soft moisture removal, and soft bake and hard bake when it is photoresist spin coating and changing it. But it is kind of really used in different text or books differently. So, do not worry about it. Here in this case you can see coating and then pre-baking. Pre-baking 90 degree centigrade, 1 minute hot plate. Again this temperature would be different depending on the photoresist that we are using. Then you use the mask, expose the wafer, then there is a PEB. PEB stands for post exposure bake, right, post exposure bake. After post exposure bake, you can just develop the photoresist, and then you can understand what kind of pattern you have. But again you see here generally what we have used: exposure, then developer, and then post exposure bake, right. So, again this can be used when you use SU8 as a material for patterning. Generally the developing occurs after exposure. There is a developing process, and then there is a post exposure bake process, okay, before we go for the further steps. But again depending on the type of the material, type of the photoresist you are using, this step is interchangeable. So, in terms of lithography, the image of the mask is projected onto a photoresist. We have seen designing optical photoresist system includes design operation of the exposure tool, the project image of the photo mask, optimization chemical process that occurs once the photoresist is exposed. We have recorded a very clear video of how to use a photolithography system in a class 100, class 1000 clean room environment. Light source may be either visible, ultraviolet, deep ultraviolet, or extreme ultraviolet, again to generate different kind of image. Three primary measures of performance for a lithography system. The first one is resolution, the minimum feature size. If you want to go for feature size which is really less than 2 micrometer, somewhere in nanometer, you go from e-beam lithography. Otherwise above 2 micrometer somewhere, generally photolithography, UV lithography can be used. Again ideally it depends on the wavelength of the light that we are using for exposing the material. Sensitivity of the photosensitive material is very important. Alignment mask is the most important thing, because the alignment mask does not align correctly with the wafer, the pattern will not be correctly, we cannot get the correct pattern on the substrate. And to if you want to further decrease the size, source with shorter wavelength, as I have told you, can be used. Traditionally mercury vapor lamps have been used as source. Now ultraviolet sources are being used. Some wavelengths are considered as standard. For example, G line wavelength is 436 nanometer, I line wavelength is 365 nanometer, used for 500 nanometer and 350 nanometer patterns. There is a KRF laser, there is a ARF laser, again used for different kind of features. So, exposure system and the optics part is the most important and the critical element in the modern lithography technique. And when you talk about that, then there are different exposure tools. The first one is contact printing, second is proximity printing, and third one is the projection printing. So, here is a contact printing when actually the mask is in contact with the silicon wafer. Here there is a proximity printing, the mask in proximity of the silicon wafer, which is coated with photoresist. And finally, projection printing where the pattern is projected onto the wafer, which is coated with photoresist. So, in contact printing, the mask is placed, which is here, chrome side down, in direct contact with the photoresist layer on the mask. So, when I was showing you the mask, right, that mask pattern that you see, where the chrome is there should touch the wafer, is in direct contact. The exposure of the resist layer takes place by light which passes through the mask. Contact printing systems are capable of high resolution printing because mask is in contact. So, the resolution is good, minimizing effect of diffraction. These systems are not efficient for printing very small features and also cannot be used for high volume manufacturing. That is a difficulty with the contact printing. Also the hard contact between mask and resist layer on the wafer can damage or contaminate the mask, right. So, these are the limitations of the contact based lithography or contact printing. In case of proximity printing, so we are now here, right, largely solves the problem of contaminating mask because it is not really in direct contact, right, and it is generally separated by 5 to 25 micrometers. That is why we call proximity. Because of separation of wafer and mask, the resolution may be degraded due to the diffraction pattern. Practical minimum feature size is order of 20 microns. And the resolution of this system improves the exposure wavelength as exposure wavelength decreases. That is when we go for X-ray lithography, which we can the wavelength 1 to 2 nanometer and can be used in proximity printing to achieve higher resolution, because general resolution is poor, but if you can increase the, if you use X-ray, then it becomes better. Both contact and proximity printing requires 1x mask, which are difficult to produce mask for reduction systems. Finally, if we talk about the projection printing, which is here, you can see projection usually 4x or 5x reduction. These systems provide high resolution, but without contaminating the mask. In projection exposure tools, the mask is physically separated from the wafer and optical system is used to project image of the mask onto the wafer. This solves the contamination issues associated with contact printing. The resolution of the projection printers is generally limited by the diffraction defects. Generally, the optical system reduces mask image by 4 to 5x times, which means that only a small portion of the wafer is printed during each exposure. That means typically steppers are used to expose the whole wafer. Since you are reducing by 4x to 5x, only the part of, you can see here, part of the wafer is exposed. That means that if you want to cover the entire wafer, then you have to go for the steppers motors, which are generally used to scan the entire substrate. So, now we have seen about the UV lithography. If we just quickly understand what is E-beam lithography or electron beam lithography, then you can see here that the electron gun is there, which will create a very high electron beam, which is passed through the alignment coil and through the blanking plates to the secondary condense lens and then limiting aperture, so that when it passes through the final lens and coils, the electron electron beam will scan the substrate which is coated with the resist, and there is a mechanical stage which will move depending on the area which we want to expose. So, electron beam lithography overcomes the size limitation of the optical lithography, because the resolution depends on the wavelength of the light used, that is in terms of few hundred nanometers, while in the electron beam has a much smaller wavelength which is close to 0.62 angstrom, with energy of 2480 electron volts. So, it can achieve much higher resolution. E-beam lithography, a very narrow beam, as I told you, is used to scan and write directly onto the wafer. This is a direct writing method and the schematic is here. I am sorry, this is figure number 1, right. So, this is a figure, or you can say figure, just figure which is shown here. The resolution of 20 nanometer can be achieved, while in photolithography, UV lithography, we are somewhere in the micrometer range. The disadvantage of this, or the limitation of this method, is the wafers has to be written individually and process is time consuming, right. So, that is a limitation. Also, it is a scanning method, while conventional lithography is a one shot exposure. Finally, this system requires a high vacuum, about 10 to power minus 6 torr. So, the process is slow and expensive. Finally, the last thing that we need to understand in E-beam lithography is backscatter of electron may affect the resolution of the process. These are some of the mask aligner that we are using in SENS, which is our central facility. Some of the videos are there. However, we have also have the video of the mask aligner that we have in our lab, and we have recorded it in detail to help you to understand how the mask aligner would work. Okay. So, this is our center facility, which is called Center for Nanoscience Engineering, which holds the fabrication, CVD techniques, RIs, DRIs, reactive etching, deep reactive etching, and the characterization facilities for the users of this institute and around. So, the mask aligner is used to align the wafer, as we have taken an example of 2 masks, right, and expose the photoresist coated onto the wafer. 3 degrees of freedom, x, y and theta. Theta is that rotation axis between the mask and wafer is provided to align the wafer to the mask. The alignment marks on the wafer is aligned to the marks on the mask prior to exposure. We have seen this thing as a quick example of this triangle and circle as a mask design. In semi-automatic system, the alignment is done manually, but in advanced automatic system, automatic pattern recognition is used in alignment system. Generally, in most of the cases in the academic world, we have the semi-automated system where it is manually aligned with the wafer. The mask is manually aligned with the wafer. But there are some high-end lithography systems, some mask aligner, where they use the image recognition to align it automatically. And then we want to see both the plus marks, right, like in our case alignment marks were plus. So, simultaneously, to view this simultaneously, we can use a split field microscope. Okay. So, here we will stop this particular section, and even though it is little bit lengthier, right, like I said, I wanted to teach you enough, but not really into depth, but not really shallow also. Okay. So, I have tried to mix and match and to show it to you what is a lithography system, and we have, like I said, let me reiterate, we have the laboratory recordings for this, specifically for this course, where how the photolithography system is utilized. So, with this I hope that now you know how the photolithography system can be used. The steps are: you take a wafer, clean the wafer, pre-bake it, then you spin coat the photoresist, then you soft bake it at 90 degree 1 minute hot plate, or depending on the type of photoresist. Then you load the mask, expose the wafer with UV, then unload the mask, develop the wafer, develop the photoresist, right, which is on the wafer. So, we say development of the wafer. Then you hard bake it. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, or again depending on the data sheet of the photoresist. And finally, after hard baking it, you can inspect the wafer, right. So, this is a lithography system. This is there are spin coaters, there are several masks, types of photoresist, exposure systems that uses UV, that uses E-beam, the advantage of E-beam over UV. So, these are the things that you should know. Now, in the next class, what we will look into is how to design different kind of etching, right, because once you have this pattern, how to etch it, right. So, there is a different kind of etching we will take into the we will learn in the next class, and then soon we will go to the fabrication of the neural implant. So, but you understand that when you want to when you want to fabricate a device, first is to understand the fundamentals of the process and to understand what are the recipes and the techniques that are used for that will be used for the neural implants. So, with that I will see you in the next class. Till then, you take care.